welcome back. So, this is our 22nd lecture, and just give a title to our lecture. I am going to call this the MPF problem. So, as I mentioned last time, what we are basically going to do is continue our discussion of the GDL. Now, in the last class what we did, so let us very quickly recap. So, I first explained what D free was, then I actually looked at how the distributive law could be used to reduce the number of computations. And then I said that to properly exploit the power of the GDL, it's the right setting from a certain perspective is the setting of semirings. So, we introduced the notion of a semiring, and we looked at some examples. Now, the way we are going to proceed is we will continue with some more examples of semirings, and after that we will define a general problem setting which the distributive law can be used to attack, and that problem setting is the setting of the MPF, the marginalize a product function problem. Okay. So, let us begin by calling this further examples of the semiring. So, this would then be example 3. Example 1 was any commutative ring with identity. Example 2 was the example from last time, and actually now that I come to think of it, I can give that a name. So, let us do that. So, I am going to go back into your last lecture. So, this was the setting of our last lecture. So, since the operations are addition and multiplication, we are going to call this the sum product semiring. Okay. So, let us put that down. So, this is the sum product semiring, and in fact I am going to copy this over to our next current lecture. Let us see. Okay. So, copy page. Let us see if I can paste page. Okay, here we go. Okay, so I have reproduced an example here, and I am going to now because our third example is in a setting similar to our second example, there are certain differences. So, what I will point them out. So, here the two operations are max and product. So, just like we had sum and product. So, this is max and product, and again in this case the range is going to be 0 to infinity, and again for the same reason, because the quantities that we are evaluating are going to be scaled probabilities. So, we will put down max and we will put down product, and not surprisingly this semiring is called the max product semiring. Again the range is 0 to infinity, and if we check to see if all the axioms are satisfied. So, we go down the list. Again let us correct this so that we have max, under max is it closed, that is if you take max of two quantities and each of the two quantities is a real number between 0 and infinity, will that also be a real number between 0 and infinity, and that is obviously the case. So, that property is satisfied. Similarly, you can check that the associative property is satisfied. How about the identity element? So, if you take the max of two elements and you want that the second element always win, then what should be the first element for this to happen, because that is the definition of an identity. Okay. So, let us just write. So, the identity under the max operation because we want that max of E A should always be equal to E. So, the question is, in this set from 0 to infinity, which real number can play that role, and you can see that that role can be played by 0. Okay. So, it is the same as the additive identity, that is if you compare 0 with anything else, the other number is going to win in the max. So, that means it is preserved. So, that means 0 serves as the identity element. So, for this reason we also have that it is closed under addition the max associative identity. It is commutative because it does not matter when you take the max whether it is A, B or B A. Under product we have already seen that these conditions are satisfied. So, and the distributive law. So, that only remains to see does the distributive law hold. Okay. So, let us okay. So, that was just the identity element, and now let us check how about the distributive law. So, what the distributive law would call for is that, is it true that so the way I find this it convenient to handle is to actually write it the way I understand it in the sum product semiring. So, it is A times B plus C is equal to A B plus A C, and this is in the sum product semiring. Okay. So, SR stands for the sum product semiring. So, analogously the quantity that is analogous to this would actually ask because addition is replaced by max. So, the question then you are asking here is it true that A times the max of B C is that equal to, now this addition is replaced again by max. So, is that equal to the max of A B and AC, that is the question. Okay. And of course, that is true, because B and C are all A, B, C are all non-negative real numbers, and of course, if you take the max of B and C multiplied by A, then you will precisely get the max of AB and AC. So, this is also satisfied. Okay. So, this is an example of a semiring. Now, our last example, and later on I will give you a reference which has many other examples of semirings as well. So, our last example is that, and perhaps what I will do here is, once again, since this has been helpful, I am going to copy this and put that down here. So, this then is our example 4, and here the operations are here you are going to work with R, the min and the plus, and so this is R min plus. So, R is now, and also there is a change in the very definition of R itself. So, R is now the interval between minus infinity and plus infinity, but including plus infinity. Okay. So, R is now the interval from minus infinity to plus infinity, inclusive of plus infinity, and so therefore, I should actually extend this all the way, and just to emphasize that it includes plus infinity, let me take it all the way to the edge of the page. Okay. So, this then is the range of our semiring. Now, let us as before check to see if the axioms are satisfied. Under minimum, is it closed? That is, if you take the min of two elements and both of them are on the extended real line meaning that I am including the point at infinity. If I do that, then is it closed? And of course, it is. So, that is actually valid. So, that is fine. Associative, you can check the identity element. So, what would be the identity element? So, what we are looking for in an identity element is we are looking for an element having the property that min of min of E and any element will actually give you back that element. Okay. So, it is not hard to see that that role is played by plus infinity. So, plus infinity plays the role that 0 played in the other semirings. It is the additive identity. Okay. So, that is one thing that we had to check. It is commutative because it does not matter in which order you take when you take the min operation. The second operation is the sum. So, this is not this is no longer the product, it is the sum. So, this for this reason this ring is called the min sum semiring. The min sum semiring. And under addition, it is not hard to see that you do have a closure. In fact, we verified that. I mean, that is just the properties of the real numbers. So, all of these properties are immediate. The identity element under plus is still 0. Okay. So, the two identity elements which in the sum product are 0 and 1 are here plus infinity and 0, okay, but you still do have these. Then the question is as before is it true that the distributive law holds? Okay. So, so since I am going to ask the same question as before, I am just going to copy from here. So, the question is, does the distributive law hold? And the form of the distributive law is a little bit different in this case, because now we have the min sum. So, the addition is the min and this is the, so here this is going to look different. So, the addition is the min. So, we will put down min of B C, and instead of product you have the sum. So, the question is it true that A plus the minimum of B and C is now this sum is the min? Is it true that this is equal to the min? So, let me get rid of this since this is going to come in the way. Is it true that this is equal to the min of A plus B, A plus C? That is the question. And of course, once you have the question very clearly laid out, it is immediate. Of course, that is true. A plus the minimum of B and C is the same as the minimum of A plus B and A C. So, the distributive law also holds. So, the answer is yes. Okay, so, we have our third semiring. So, now we have seen 3 examples of semirings apart from the usual examples which come from rings. That is, we looked at the sum product semiring, we looked at the max product semiring and the min sum. These 3 are the ones that you typically encounter in coding theory. I think we in particular will make use of the first 2, that is, we will make use of the sum product and the semiring. Now, I mentioned at the outset, in fact that was the title of our lecture. The title of our lecture is the MPF problem. So, we will get to that now. The MPF problem. So, what is the MPF problem? So, first of all, MPF stands for marginalize a product function. And the meaning will become clear once we look at some examples. So, the setting is the following. There is a universal set S which is 1, 2, to n, there is an associated set of variables which we will write as x s, which will be x 1, x 2, x n. Each x I will take on variables from an alphabet a I. So, this is the alphabet of the variable x I. The size of this alphabet a I will be q, and I could write q I, and in fact we will. Okay. Then, okay, so that's that. In addition, we have subsets. We have subsets S j of S. Okay. So, if you have, for instance, a particular S j whose elements are, let us say, I 1, I 2 to some I sub n sub j, then now this is a subset of S. If we want to refer to the variables corresponding to this subset, we will actually use the short form notation x sub s sub j, which we will mean x of I 1, x of I 2, x of I sub n j. Okay. So, now we will be a little bit sloppy in our terminology, and we will actually refer to both of these interchangeably as local, excuse me, I think I need a darker color here. So, let us pick this. So, we will refer interchangeably to these as local domains. Okay. And if I want to refer to the alphabet associated to, let us say, this local domain, then I will accordingly use the notation. So, A sub S sub j is the alphabet from which x sub S sub j is drawn. Now, it may look a little bit confusing, the notation, but as we look through examples, it will actually turn out that it is not complicated at all. And similarly, if we want to refer to the size of this alphabet, we will simply write q sub S sub j. Now, okay, so let us just recap that. So, what we have is a universal set, and you can think of this as a set of subscripts, a universal set of subscripts. You have a set of variables, in some sense the universe of all variables, and there are n, little n variables in all. Each variable takes on values from its own alphabet. The size of the alphabet is q I for the ith variable. Then we also have subsets of S, which we will call local domains, and the total number of them is actually m. So, let me put that down here. So, j varies between 1 and m. So, there are m of these subsets, and we have introduced some notation to talk about the alphabet of the associated subset of variables. We are going to call them local domains. So, this is the alphabet of the jth, this is the alphabet of the jth local domain, and that alphabet has this size. We are almost done with the description of our setting. We also have what are called local kernels associated with each local domain X S j is a local kernel which we will call alpha sub j of x sub j. So, that is the jth local kernel. And what does this do? So, this alpha sub j maps x sub j onto R. What is R? Well, R is where our semiring comes in. Okay. So, the values of alpha are in some semiring R. To begin with, you can think of it as the max product semiring, that is, it is the set of all non-negative real numbers, and the operations of the semiring are the usual addition and multiplication. Then there is something called the global kernel. So, the global kernel is a beta of x of s is the product j goes from 1 to m of alpha sub j x sub s sub j. Since there are m local kernels, you have a product of m terms, and that is called the global kernel. And finally, we have something called the jth objective function, so the jth objective function is beta sub j of x sub j. What is that? This is simply the marginalization. Okay, so I think that's looks a little cramped there. So, let me write this out on the next, we'll write it out on the next page. So, the jth objective function is the marginalization. So, that is given by the sum over x sub s sub j complement of beta of x sub s. Now, what does s sub j complement means? This is simply the set of all elements in S. So, it is the set theoretic complement. So, it is just all the elements in the universal set S apart from those in S sub j. Now, why is this called a marginalization? It is called a marginalization because just like when we deal with probability, okay, so let me just make a slight detour. So, in probability, when we write that p of x 1 is equal to the sum over x 2 of p of x 1 x 2, then that is an instance of marginalization in probability theory. Okay. So, since let me just do one thing, since this is really an aside, let me put it on the next page and just say, put this down as an aside. Okay. So, marginalization is used in the sense of probability theory, that is, you sum over certain variables, so that what is left is a function in the remaining variables, right. So, now the meaning of MPF should become clear, because you are trying to marginalize a product function, right. So, in our case the product function is the global kernel. So, this is our product function, which is also our global kernel, and you are marginalizing because you are summing over a subset of the variables. And again, you have as many objective functions as there are local kernels. So, there are this many objective functions. Now, that might seem like a lot to absorb in terms of notation, and that is true, but I think once we get to examples it will all become clear. So, here is our first example. One, the 8-dimensional Walsh-Hadamard transform. Now, the Walsh-Hadamard transform is similar in nature to the discrete Fourier transform. It is a little bit different because the different set of functions are involved, but the Walsh functions do turn up in several settings. For example, in your CDMA, you know that whenever you take a Fourier transform, the discrete Fourier transform, basically what the discrete Fourier transform does is that it takes a time function, multiplies it by a unitary matrix, which is the Fourier transform. Okay. So, here we are dealing with a different unitary matrix, and as you all know that if the rows or columns of a unitary matrix are pairwise orthogonal. So, the Walsh transform is also defined in terms of a unitary matrix, and the rows of the matrix are also pairwise orthogonal. The matrix is particularly simple in nature because it consists of only plus and minus ones, and it is these functions that actually show up in the IS-95 CDMA original IS-95 CDMA system, because there these functions were what kept separate the signals of the different users on the downlink. Okay. So, with that as motivation, let me write down the expression for the Walsh transform. So, the transform carries out the following computation. It says that f of x4, x5, x6 is the sum over x1, x2, x3 of little f of x1, x2, x3 times minus 1 to the x1, x4 minus 1 to the x2, x5 minus 1 to the x3, x6. So, this is the computation that it actually carries out, and let me just, so that well, let us do one thing first. I first want to actually point out that this falls into the setting of a marginalizer product function. Why is that? That is not hard to see, because here what you have is the product of several functions. So, these are the local kernels, you are multiplying the local kernels, and then you are marginalizing with respect to a certain set of variables. So, this is an example of an MPF problem. So, let us make a note of that. This is thus an example of the MPF problem. So, how is it an example? So, here your universal set is just 1, 2, 3, 4, 5, 6. So, x sub s is therefore x1, x2, x3, x4, x5, x6. Okay, so, this is your universal set and the corresponding local domain. The semiring, so this is the sum product semiring. I have to be a little bit careful here, I am sorry. So, here in fact this is not quite the sum product semiring, because the values can take on negative values. So, in fact this semiring is just the field of all real numbers. Of all and as so this is just nothing but R with a double vertical bar, and then so it remains to identify the local domains. So, going back to this expression here, you can see the local domains. So, one domain is, so this is typically what you do in practice. You are presented with a certain computation, and then what you would have to do is you would have to actually translate it to the setting of an MPF problem and then go about solving it. Now, we have not come to the part where we actually try to solve it. So, we are trying to now make the connection between this and the MPF setting. So, this is marginalization, this is the product function. So, therefore, these must be the local kernels. There is a kernel x1, x2, x3, x1, x4, x2, x5, x3, x6. Okay. So, let us put those down. So, you can say that S1 is 1, 2, 3, x S1 is x1, x2, x3, S2 is 1, 4, x of S2 is x2, x4, S3 is 2, 5. So, if x of S3 is x3, x5, S4 is 3, 6, x of S4 is sorry, that should be 2 here. This is x3, x6. Okay. So, we have got 4 local domains right now. So, we have the local domains that correspond to 1, 2, 3, 1, 4, 2, 5, 3, 6. But we are not done. The reason for that, if you go back here and look, is because we needed in the problem setting to be evaluating certain objective functions again at a local domain. So, even the variables that appear on the left hand side must correspond to a local domain. Okay. So, that forces us to introduce another local domain, which will be S5, which will be 4, 5, 6 associated to X4, X5, X6. But now, okay, so then the next question is, well, what are the local domains? Okay. So, let us put them down here. So, alpha 1 x f s 1 is f of x 1, x 2, x 3, and similarly alpha 2 of x s 2 is minus 1 to the x 2 x 4. Okay. So, we are looking at this computation, and right now we are looking at x 1 x 4, sorry. So, that should be, this should be x 1 x 4. That is your second one, and similarly we can write down the others. Alpha 3 x s 3 is minus 1 to the x 2 x 5, alpha 4 x s 4 is minus 1 to the x 3 x 6. But then here we have this other local domain. What kernel shall we associate with that? Because if you go back to the expression here, there is no local kernel that is present here, and yet in the MPF problem you do need to be multiplying all the local kernels together before you proceed to marginalize. So, the answer is quite simple. You just introduce somewhat artificially a local kernel, and you say that alpha 5 of x s 5 is just 1. Okay. So, now so this way you have not affected the product, and yet it now satisfies the property that you have the left hand side variables also, collection of variables also as a local domain. Now, it is perfectly in the setting of an MPF problem. Okay. And again, in going through these examples, what we are going to do right now, our objective right now is a little bit limited. All that we are going to do is just take a computation arising from whatever origin and then put it in the setting of an MPF problem. Later on, we will actually go ahead and see how one would solve it. Just to give you a slightly better feel for the Walsh transform, let me put it down in its matrix format. So, in its matrix format, it would look like this. It would actually, you would have at the heart, you would have an 8 by 8 matrix. Let us see how I can do that. So, perhaps I can fit it in here. Okay, so that would work. So, I have so it would be a computation like this, just so that okay, so never mind. So, on the right hand side I will have the various values of the function f. So, I will have f of 0 0 0, f of 0 0 1, f of 0 1 0, f of 0 1 1, all the way down to f of 1 1 1. And that reminds me that I forgot to tell you something that was important, namely that these variables, the alpha bit of the variables is something that I forgot to actually tell you. So, let us see if I can insert a page and fit that in here. Okay. So, as far as alphabets go, the alphabets AI. So, each alphabet AI is just the binary alphabet 0 1. So, the same the alphabet is the same for all I between 1 and m, and of course, the size of each of these alphabets is 2. Okay, so, that is as far as alphabets go. So, that is the reason when I am writing down a matrix version of this computation, I have all these zeros and ones over here, and here on the left hand side what I am going to be computing are f of 0 0 0, f of 0 0 1 down to f of 1 1 1. In the middle I have what is called the Walsh matrix or Hadamard matrix, and the entries of this matrix are simply there is a specific pattern which they follow. So, I am going to draw some dividing lines which makes it easier. Okay. So, it turns out that the entries are 1 1 1 minus 1, 1 1 1 minus 1, 1 1 minus 1, minus 1 minus 1 minus 1 1, and so on. Okay. And here again okay. So, never mind how I actually obtained these entries. There is a simple pattern. If you stare at it, you will figure it out. The reason I just wanted to introduce this was simply because if you replace each one with a pulse train, okay, with a pulse train, a pulse with positive height and a minus 1 with a pulse of negative amplitude, then you will get the Walsh functions that are employed in CDMA. So, for example, so this is purely for motivation, we will not be using this. So, let me take this last Walsh function that I have here, then this would be associated with a pulse train, and that pulse train will go positive, then negative, and then again go positive, negative, positive, positive, and negative. So, this is the pulse train that this particular string of symbols represents, and it is these functions that are used to keep the different users in a CDMA forward or downlink separate. Okay. But this is again, I said, purely for motivational purposes, just to get you interested in this computation. So that is kind of an example that the GDL can actually compute. So let us move to example 2. Example 2 is an example from coding theory. So, we will look at a specific error correcting code. We will look at a 742 linear block code, and we will specify it in terms of its parity check matrix. So, the parity check matrix H of this code will be given like this. So, this is the parity check matrix, and so you can see that this is a 3 by 7 matrix as required. Recall that whenever we write 742 linear code, what we mean is that the code has block length n, dimension k, and minimum distance d equal to 2. Now, if you still remember some of the example codes we looked at earlier on, you might say, okay, this is a 742 code, but don't I remember you telling us or showing us a Hamming code whose parameters were 7, 4 and 3, which means that the Hamming code in relation to this code, which I am showing you now, has the same block length 7. The Hamming code has the same dimension, which is 4, but the minimum distance here is 2, whereas the minimum distance of the Hamming code is 3. So, you might say, well, why is this code interesting? It has minimum distance which is less than that of the Hamming code. And in fact, that is typical of this of the way coding theory has gone in recent years, because the emphasis has gone away from trying to find the code that is structurally the best to one that is easier to decode. So, this code, while being not as good as the Hamming code, it does have a big advantage over the Hamming code, namely the advantage of being easier to decode. Okay. So, this is fairly typical. Now, also the setting in which we are going to look at this code is that of the binary symmetric channel. So, we are going to assume a binary symmetric channel, which we can view in one of two ways. Either we can view it like this, input 0 1, output 0 1 with crossover probability epsilon, or we can also view it as one in which you transmit a code word x, you receive y, and the channel introduces an error vector e, and this addition is of course modulo 2 and addition here is modulo 2. And it is component by component, and this x actually is drawn from our code. Okay, so, script C stands for the code. What we would like to do is formulate the problem of carrying out maximum likelihood decoding, code word decoding of this code as an MPF problem. So, that will be our goal. Formulate the maximum likelihood decoding, and I should say perhaps I shall let me spell this out just to eliminate any confusion. Formulate the maximum likelihood code word decoding problem as an example of MPF computation. Okay. So, I think we just have a couple of minutes left, so perhaps I will summarize. So, what we have done is I have defined what something called an MPF problem, and which stands for marginalize the product function, and our goal is to actually show that problems of interest, decoding of codes of interest can be formulated as an MPF problem, and that the generalized distributive law can be used to solve this problem. We began the lecture by some further examples of semirings. That was where we had left off in the previous lecture, and then after that I gave you the general setting of the MPF problem, introduced all the notation, and then we started looking at examples. The first example that we looked at is the 8-dimensional Walsh-Hadamard transform, and then we have just moved to discuss the second example, which had to do with maximum likelihood code word decoding of a block code. We will continue next time. Thank you.